Hello, my friends. I would like to welcome you all from Israel. My name is Oleg Butkovsky. I'm a researcher at the Weierstrass Institute, Berlin. But right now, I'm trying to hide from Corona here in Israel. So let me start by sharing the slides of my presentation. So I just would like to warn you that this is my really first experience of trying to record myself, but I hope that things will go smoothly, and I hope that you can see the screen now. And I also hope that Zoom will record me properly. So I want to discuss with you today our very recent progress on regularization by noise for partial differential equations. And this culminates our around 5-year work with Siva Thriya, who is in Bangalore in India, Hoa Le, who is in Technical University Berlin, and Leonid Mitnik, who is in Technion in Haifa in Israel. And myself, as I said, I work at the Weierstrass Institute Berlin. So what is this phenomenon about? What is regularization by noise? Let us start with something very simple. Let us consider an ODE x dot equal b of x. If the function b is Lipschitz, then this equation has a unique solution. This is easy. If the function b is not Lipschitz, but only Hölder, then this equation has a solution, but it might be not unique. It might be that this guy has infinitely many solutions. For example, let us think about x dot equal root x. Then this system indeed has infinitely many solutions. But at least we know that one solution is guaranteed. And now, if the function b is only bounded, then it can happen that this equation might have no solutions at all. For example, if we look at the equation x dot equal minus signum x, we see that signum is not even continuous, then it is easy to convince oneself that this equation has indeed no solutions. So the picture here is relatively clear. If the function is, so if we denote by gamma the Hölder index of the function b, then what do we see here? We see that if b is in C gamma, and gamma is 1 or larger, then it is guaranteed that this system has a unique solution. If gamma is between 0 and 1, then it is guaranteed that the system has a solution, but it might be that the system has infinitely many solutions. And if gamma is only 0, then nothing is guaranteed. It might happen that there is no solution. Okay, so this was relatively easy, straightforward calculus 104. What is not easy and not straightforward was an important breakthrough achieved by Zvonkin and Veretennikov in the 70s, who suggested to consider stochastic differential equation and add to the equation that we have just discussed a random noise. Okay, so now we consider dxt equal b of xt dt plus dwt. And the result is as follows. So if the function b is only bounded, then this equation has a unique strong solution. So let me just compare. So here, for uniqueness of solution, we wanted b to be Lipschitz. And the result of Zvonkin and Veretennikov shows that once the random noise is added, then one can significantly relax the requirements for the function b. And in particular, if b is only bounded, then this is already enough to well-posed. And this phenomenon is called regularization by noise. So we have an ODE, or we have a system, we have a deterministic system, which is not well-posed, like this equation when b is, I don't know, root x. You add a random noise, and then the system becomes well-posed. So this is regularization by noise. Now, more recently, Bass and Chen in 2001 showed that in dimension 1, which is very special, you have existence and uniqueness of strong solutions already when b is a distribution of regularity minus 1/2 or larger. Now, of course, it is not so clear what exactly do we mean by distribution. What exactly do we mean by distribution applies to x, right? So if b is a distribution, what do we mean here by b of x? Not so clear, but we will go back to this maybe in 5 minutes, but we will understand it in the sense of approximation. But anyway, the point is that in dimension 1, one can especially relax the conditions on the function b and have like really good regularization by noise. Now, of course, there is nothing magical or special in the fact that we choose W to be a Brownian motion. There is nothing, it is not so important that it's a Markov process or a martingale. And indeed, some further extension, for example, for fractional Brownian noise were achieved by Catali and Gubinelli, and more, like some recent progress can be found in the paper of Gagliati and Gubinelli. And so from what I understood, Lucio is giving a talk at this conference, which is highly recommended to see. And now, in my talk, I want to study the same phenomenon, regularization by noise, but now for partial differential equations. What do I mean? I mean that I would like to consider a stochastic reaction diffusion equation with bad drift. So B now is in C gamma, gamma is less than 1. And as I explained before, it is interesting to consider, to include also the possibility when gamma is negative, so when the drift B is a distribution. And I want to study an equation, du over dt equal Laplace u plus B of u plus space-time white noise. Okay, so we can equip this equation with periodic or Dirichlet or any other boundary conditions that we want. This will be not important for us. But what would be important that we would be also interested very much in the case where B is a distribution, for example, a delta distribution. And the first thing that we need to discuss is what exactly do we mean by a solution to this equation? Because if B is a distribution, as I said, B of u is not a priori well defined. We need to explain what do we mean. Okay. And we would like to suggest the following very natural definition. So we say that the continuous process u solves this equation if for some process k, we'll talk about this k in a moment, we have the following identity. So utx equals pt applied to u0. So pt for me is a Gaussian kernel on 0, 1 equipped with your favorite boundary conditions. Plus, again, Gaussian kernel applied to the space-time white noise. So up to here, there is nothing unusual. Plus this process k. So what is k? We want k to be morally pt applied to b of u, but this is not well defined. So we say that for any sequence of smooth functions bn converging to b, so for example, one can take bn to be some smoothing of b, some heat kernel applied to b. We want that pt minus r, so the Gaussian kernel applied to bn, converges to this kt of x. Okay, so somehow, if gamma is bigger than 0, so this is just the very standard definition of a mild solution, because then we don't need all these tricks, so then this would indeed converge to b of u. And if gamma is less than 0, then we found it's also very natural, because this extends the corresponding definition of Bass and Chen. So as I mentioned before, Bass and Chen were the first who suggested how to define a notion of a solution to equation where you have a distribution of u. And so their idea was similar. Okay, so now at least it is clear what do we mean by a solution to this equation. Okay, so now what do we know about regularization by noise? Okay, the first case is when b is a Lipschitz function. Then everything is very clear. This equation has a unique solution even if there is no noise. So this is clear. A breakthrough was obtained by Giongi and Pardue in '93, who showed that this equation has a unique strong solution already for the case when b is bounded. But they have used some comparison theorems. And then there was also a very interesting result, very recent result by Bonin, Bachet, and Zambotti, who showed that if b is a delta function, then there exists a weak solution to this equation. So they didn't show uniqueness or existence of strong solution, but they somehow hinted that it might be possible to extend the results of Giongi and Pardue beyond 0. So this is what we can learn from them. And to achieve this result, they used a very sophisticated theory of Dirichlet forms, but unfortunately, this theory didn't allow them to show uniqueness. Okay, so we know that this equation is well posed as long as b is bounded, as long as b is bounded function. And we also, and there is some hints that something interesting might be going on below 0 when b is a distribution. And now let me present you our main result, which somehow fills this gap. So now assume that b is C gamma, when gamma is bigger than -1, so exactly here, or b is a Dirac delta function. then this equation has a unique, strong solution. So somehow, so what did we do? First, we managed to cover this interval. So we now have well-posedness when b is in C gamma, gamma bigger than -1. And we have also proved the conjecture, because Boolean Bashains and Botti, they conjecture that everything is not, there is not only weak solution, that there exists like a normal strong solution, which is unique. So we have proved their conjecture. And indeed, we have shown that if b is a delta function, or it's not so important if b is like any measure, so b should be a derivative of a bounded function with bounded variation, okay? So in this case, this equation has a unique, strong solution. So now the picture looks like this. Now we have completely filled this interval. And the case where you put here a delta function is called skew stochastic heat equation. It is important for applications to random interfaces. And unfortunately, I don't have much time to talk about now, but I will be very happy to explain it during our live sessions. Maybe also I don't have much time to talk about the proofs. Let me just show you that something naive, right? So if we have two solutions, x and x tilde, like how one can prove it, right? So we consider their difference. And then we want to show that this guy, the difference is 0. So we have that z is their difference, the noise cancels. But because b is only a gamma Hölder function and gamma is less than 1, we get something like this, which is like, does not imply that z is 0 because it's not good for Gronwald. What we want to get instead, so we don't want this, what we want to get instead is somehow we want to trade the power of t, right? So here was somehow t to 1 times this protest to power gamma. And we want to trade the power of t, want to have it t to delta, and then this protest to power 1. So we want to show, and this is called in the literature Krylov type bound. So we want to show that, for example, if z is constant, at least like the very minimum that we want to show is this Krylov type bound. So that the function b, which is only gamma Hölder continuous of x plus z minus b of x, behaves like, so that this guy is actually Lipschitz, okay? And in the for the SDs, as I showed you before, the ideas of Zvonkin and Vertenikov was to use eta formula. And here we don't have any reasonable eta formula. And so what do we do? Let me now, so this is, I'm like going maybe a little bit too fast, but again, I will be very happy to answer all your questions and to talk about this in details during our Q&A session. So for SDs, indeed, people are using PDE methods via eta formula. If there are SDs driven by fraction bounding motion, then people use nonlinear Young integrals, some deterministic suing Girsanov theorem, and all of these techniques for us, they were not available. There is no eta formula. Girsanov theorem is really bad, and this nonlinear Young integral, not so clear what to do with them. And so we developed a very new technique. It's called stochastic suing with propagators and random controls, which extends to the stochastic context the ideas of Tyndall and Gubinelli, who did suing with propagators, which extends the ideas of Fritz and Zhang, who studied suing with random controls, and we extended all this to stochastic context. And I would like to also recommend you in the end the talks of Hoale and Mate Gerencher at this conference, as well as the talk of Lucio Gagliati. But Hoa and Mate, they are talking about the stochastic suing maybe in more details. And then you can get some, how it works in the simpler case. And then, of course, I will be very happy to answer your questions about what exactly we have to do. Okay, so I hope you enjoyed this talk. I hope that I was recorded. And it was lots of fun. And see you all very soon during these online sessions. Bye-bye, guys.